All right, on this one, you're going to want to make sure you leave yourself a lot of space where you're taking notes. We're going to need to make a chart. So leave yourself lots of room. It's going to be a 5-column chart, 4-row. So here we go. Whoop, whoop. Over here, we're going to have on the top variables that are affected. We're going to have what the graph looks like. After that, we'll have how the variables relate to each other. We're going to have what the equation looks like in variable form. So this will be variable form. And a little bit over here, we have what the final equation looks like. Whoop, 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 whoop. And then over here on the left, what we're going to have is the name of our laws. The first one is Boyle's Law, B-O-Y-L''S. Next up, we have Charles' Law. Below that one, we're going to have, and get your laughs out now, the Gay-Lussac Law. And finally, at the bottom, we have Avogadro's Law. I always spell his name wrong. And there we have it. So first up, Boyle's Law. What variables does it deal with? This one is pressure and temperature, which means, my apologies, pressure and volume, which means that temperature, which is why I wrote that, temperature and number of molecules is going to be held constant in this. So you can think of this as kind of like a closed tube or a closed syringe where you can push on one end, you can make it squeeze tighter, but the pressure is going to go, well, we'll get into what happens here. If I put a graph with pressure and volume, if I decrease my pressure, what happens is my volume has to increase exponentially. Or if I squeeze my volume really tight, my pressure goes up. So I get an inverse relationship. P goes up, V goes down. They're inversely proportional. So PV equals a constant, or what you can say is that P is proportional to 1 over V. It's an inverse relationship. So when we write out Boyle's Law, we get P1 V1 equals P2 V2. This just means the pressure and volume multiplied by each other in a before state is going to equal the pressure multiplied by the volume in an after state. If I increase my pressure later, that means my volume has to go down. Next up with Charles' Law, we have volume and temperature as our variables with pressure and number of molecules held constant. And on this one, what we're going to see is that, hold on, don't move. I just realized that you guys can't see this side, so I'm going to move you over just a little. Almost there, almost, got it. But in this one, volume and temperature are going to be your variables. So if we look how volume is affected by temperature, if I increase the temperature of something while holding its pressure constant, well, pressure is going to go up if I warm it up, right? So I need to increase the volume. So we'll see a linear relationship here. That means if temperature goes up, volume goes up. So what we find is that volume over temperature is equal to a constant, or what it says is that volume is proportional to temperature. This lowercase alpha represents proportional. So when we write out Charles' equation, we get V1 over T1 equals V2 over T2. Meaning if I double temperature, I need to double my volume as well. Next up, we have Gay-Lussac's law, which is pressure and temperature. In this one, we're going to find a very similar situation to volume and temperature. If I keep my volume constant, it means I have like an enclosed container, but I heat it up, that pressure is going to go way up. That's how pressure cookers work. You have a set volume, you increase the temperature, and then you way increase the pressure as a result. Same idea here. If temperature goes up, pressure goes up. They're going to be linearly related as well, where we have pressure over temperature is equal to a constant, where pressure is proportional to temperature. So this one, very similar, not V. P1 over T1 equals P2 over T2. And finally, this one is less of an AP Physics one and more of a carryover from chemistry. You don't really see this one as much, but in this one we have your number of molecules and volume being compared to each other. So in this one, if we keep temperature and pressure held constant, then as we increase the number of molecules, they should take up the same amount of space. That one's fairly obvious. Back in the day when there wasn't a lot of science written down, anybody could put their name on any formula, even if it was like everyone's like, bro, that's easy, obvious. But this just means that volume over your number of moles is going to be constant, so volume is proportional. And what we get here is V1 over N1 equals V2 over N2. Cool beans. So now that we've got these four equations, you may start to notice, hey, I see volume in a lot of these. I see pressure. I see temperature. Maybe there's a way to put them all together and relate them. And when we do that, what we get is called the combined gas law. Now, the true combined gas law has everything on it. So that'd be P1 V1 over N1 T1 equals P2 V2 over N2 T2. That's the one you'll see in chemistry. The one that is on your physics equation sheet will only look like that. Now, you should hopefully understand the relationship there if they ever ask you a problem, like what happens if I put more molecules in the container but keep everything else the same, then you should be able to figure it out from that. But just keep in mind, these ends don't appear on your equation sheet. Now that we've got the combined gas law, which this is really good for when you have an equation where, hey, I've got some system at the start, I have some system at the end, but I want to know how one of them changes. For instance, like I want to say, what's going to happen to my pressure if I double my molecules, halve my temperature, and quadruple my volume? Well, this will let you figure it out. So this is good for when you're changing states. But what's going to happen when you just want to know one variable about an equation at a given state is what we call the ideal gas law. And for this one, it only works at conditions where all gases behave similar to ideal gases. That's why they call it the ideal gas law. So it only works when our temperature is low and or our pressure is high. That's still on there? Beautiful. And what our equation is going to look like is PV equals, and these are two separate ways to do it, nRT or equal to NKB, sorry, this should be a capital N, KBT. Remember, little n, number of moles. This one, number of particles. So there's going to be a lot more particles than moles. So this has got to be a really small number to make up for that. This would be a more reasonable number. Both of those are on your equation sheet as constants. But I'll write them out here for you. R is the universal gas constant. So univ gas constant. And it is 8.314 joules per mole Kelvin. The units on here are important because it tells you when to use what. You see moles down there? That's going to help you know you need to use R. KB is the Boltzmann constant. And Boltzmann constant is 1.38 times 10 to the minus 23 joules per Kelvin. Notice there's no representative unit here because molecules is not a unit that we use normally.